Of Kensington College, continuing our lessons on C++. We're talking today about pointers. What is a pointer? Basically, a pointer is a variable which holds an address. Why are they important? Take this example. We've got here a couple of strings, which are in two strings here. We want to actually swap the strings in a process of sorting. The strings might be very large, and so to allocate them in memory would take a bit of doing. Making sure one is bigger than the other and so on, and allocating space. So what we can do is take the address of the string. Now if you look here carefully, it's in hexadecimal, 0x0138 such and such, the 0x indicating hexadecimal, and we have another hexadecimal address here for the second string. So rather than swap the strings, we could actually swap the pointers to the strings. So we need to discuss what a pointer is. A pointer is a variable which holds an address. This is how we declare a pointer. It reads from right to left. We say a pointer, PTR, the variable PTR, could be any name at all. Asterisk means is a pointer. But strangely enough, we have to say what it's pointing to, what type, T-Y-P-E, what type it's pointing to. That could be a float or a double or a character, and so on. And we'll see why we have to do that in just a moment. So let's make an integer variable. Int I is given the value of 5. What I'm going to do is to set my pointer equal to the address of that variable, where it's located. I'll put ptr equal to that address. And the notation for address, if you're not aware of it, is equal to equals ampersand I. Ampersand means the address of. So the address of I is set equal to our pointer ptr. I might run that code, so I'll put a breakpoint in here and run the code down to that position. And what I might also do is take a look at the memory window. So if I go to debug Windows and then look at the memory 1. Okay, so here's the memory window. We're going to take a look at where I is stored. So I can take a look here, and it says here that ptr, well, it's just hasn't been assigned yet. So it's got 0xccc, so it's just a random initialization, which is not initialized at all. So let's see, if I press the F11 key to single step this, it then gives me an address. You can just see that, so I'll go and copy that address, and then the Control C, and then I'll go over to my memory window and paste that in V, and then press enter, and there you can see my variable, integer variable here. This is where I is located, but this is the address of I, which has actually been allocated to this ptr variable. So once again, just to how I declare a pointer, ptr is a pointer. That asterisk is very important. You'll see later on that it's ambiguous actually, and it causes a lot of trouble. But for the moment, it means is a pointer. Please take a look at that. ptr is a pointer to type integer. So just looking over here, there's the address of I, which has been assigned to ptr. So it says here ptr is the address of I, and there's my integer. Now it's back to front, and this is the way that integers are stored. They're called little endian, where the least significant byte is up here, and it's completely back to front. So you'd think that the 05 would be here. It's 4 bytes long, by the way. Here's an integer. You'd think the 05 would be here, but in fact it's up the other end, a little endian notation, which apparently is a more efficient way of allocating integers to memory. Returning to our declaration of ptr, we said ptr, once again, is a pointer to type int. Now that could be float or so on. Now why is it important to say what it points to? In other words, what is located here at the address of this pointer here? The answer is, let's say we considered something like this, ptr++. Now you're going to say immediately ptr is increased by 1. It's not. It's actually increased by 4. Why? because we know that the next integer will be stored lower in memory, actually. Up here, notice that's lower in memory. But anyway, the next integer will be stored somewhere up here, which is 4 bytes along from the previous integer. Well, let's see if that's true. I'm going to stop that code and run the code once again down to the breakpoint. And we'll take a look at the address of PTR. In this case, it hasn't been initialized, so I'll press F11 to give it the value. It says it's changed, by the way, from previously. If you notice very carefully, that 30 here. And then when I F11, the value now is 34. So it's actually gone up in memory. If I just take a look at it, it says 34. So it's gone up by 4 bytes. So the pointer itself has progressed. If we're iterating through some pointers, then it's progressed by 4 bytes along. So it'll pick up the next. So it doesn't increment by 1. It increments by 4 in the case of an integer. That's why we have to say what the pointer points to, what type it points to. Let me say that this time we're going to have a character. We'll call it I for the moment. The character is some character, and then we're going to put a pointer to the character, and then we're going to increment the pointer and see by what increment. Well, let's take a look at the value of the pointer at the moment. Well, it's got the value of 8b. You might just see that 8b at the end here, 8b. So let's see what happens when you increment the pointer, F11, and now take a look at the pointer address, and you can see that it's 8c down just there. So in this case, it's gone up by 1. I would have expected it to have gone up by 2. It usually goes up by pairs, but okay, so it's certainly incremented by 1 or 2, as distinct when we have an integer which is incremented by 4. And if you try a double or a float in here, then you can see that it will be incremented by corresponding amounts, for example 8, and so on. So that's why we need to say, once again, PTR is a pointer, in this case pointing to a character in memory. So returning to our previous code, when we had an integer variable, we assigned our pointer to the address of the integer. Let's say instead of initializing I here, I'm going to try and initialize it using a pointer. Now the notation for that is this. And this notation means the contents of PTR is set equal to 5. Now take a look here and you'll see why pointers can be confusing. Well, they are confusing to people. The reason is this asterisk here now has a different meaning. We need to focus very intensely on this. In this case here, this means that the contents of PTR is set equal to 5. But in this case, it means PTR is a pointer to type int. Now, I guess the criterion is that there's nothing here on the left in this particular case. There's nothing to the left of that. When there is something to the left, like in here, you're saying that this means now is a pointer. But if there's nothing to the left, as there is here, that means the contents of PTR equals 5. So to reiterate, in this case, the asterisk here means is a pointer, and the asterisk here means the contents of. So once again, PTR is a pointer to type integer. In this case, the contents of PTR is set equal to 5. So let's see if that indeed works. I'm going to run it down to there and take a look at the memory window. So running the code to this breakpoint, I can pick up the address. If I hold my mouse on here, I should be able to pick up, there we go, I can pick up the address which is stored in the pointer. I'll copy that and paste that into here, and I can see the location here. So this is the address which should be stored, which is stored in the pointer PTR, and this is what is at the address, which is just some random stuff at the moment. But let's see what happens as I press the F11 key. You'll see that the value of 5 has actually been stored into that address. So once again, the contents of PTR is set equal to 5. To emphasize once again that the ambiguity which causes people problems is because this asterisk has got two different meanings in two different places. I don't know why they really didn't use some different symbol. Would have caused less confusion, but they've used the same symbol, asterisk, in both cases. So, but the asterisk means two different things in two different places. Incidentally, the asterisk could be placed in either position. We could have this asterisk here could be placed there, for example. That would compile just as well, but by convention we put the asterisk next to the type that we're qualifying, in this case the integer. So the asterisk would go next to the int, but this asterisk will always go next to the pointer value when it means the contents of PTR is 5. PTR is a pointer to an int, and the asterisk is usually placed next to the type. By the way, there's something quite glaringly wrong here in that I ought to have deleted the PTR. Now that means clear the content, make PTR available. Now that address that we saw in memory will now become available to the rest of the program. It won't cause an error in your program necessarily, but the memory hasn't been deallocated. So that means that subsequently it could cause some errors, a potential time bomb, literally, for your code if you don't delete your pointer. When we say delete PTR, it doesn't actually delete anything. So there's our memory location here where the 5 is stored. All it does is says that this memory location is now available for something else. But if we don't do that, we get what we call a memory leak. A memory leak is when you don't deallocate memory, and this can build up and cause problems later on. We've been dealing so far with what we call raw pointers because the problem of deletion is quite significant, because we might actually forget to delete our pointer. Now this might not necessarily because we forget. There might be an exception in your program and so on. There are ways in which they are not deleted, and so this brings us to, in what we call modern C++, to define a smart pointer. Now a smart pointer is really a class which contains a raw pointer, and the class will get deleted automatically when it goes out of scope, so the pointer will automatically get deleted as well, so it's a lot safer. So very roughly speaking, within C++, we define this within C++. We use this unique pointer where this class actually contains a raw pointer, which we've been talking about, and then very roughly speaking, we then use that to declare a smart pointer, but then we can use the same sort of operations that we normally do. So that will basically avoid memory leaks, but for the moment let's just focus on raw pointers, in that you'll see them being used in legacy code. But in future, if you're going to be writing new code, we ought to start using smart pointers. Recall that when we ran the code down to this point here, we set the contents of PTR equal to 5. So we've set our integer value, and this is the value of the pointer variable. What about, and we discussed incrementing the pointer. That will mean we'll be incrementing it by 4 to take it on to the next memory location, which indeed will be here. So that, what about therefore if we set the contents of that, as equal to, well, we need some parentheses here because we need to do that operation first. We need to increment our pointer, and then we'll set it equal to some value, and then we'll run the code again and run it down to that breakpoint, and let's just see that that does place the value of 8 into the next memory location. So once again, I need to pick up the memory location by holding my mouse on there and picking up the address. I'll copy that and paste that into the memory window, and then press the enter, and we're about to set it equal to 5. So if I press the F11 key here, you should find that that value is set to 5. Now what about the next line? That should set the next memory location equal to 8. So if I press the F11 key, you'll see that the 8 has indeed been placed after the 4 bytes along. So this has incremented the pointer by 4. Incidentally, I've incremented in using the prefix operator. You might like to think of the effect of using the postfix operator. It actually will mean that this gets incremented after it's been allocated. But that's really beside the point. What I do want to show you is this, and this will have the same effect as incrementing the pointer. Now that's a bit strange really, but let's just see if that works. Well, when I run the code and single step it down to that, you can see that 8 has been placed into the next memory location. So you see the PTR put the value of 5 in this, and then we incremented our pointer, but that's very deceptive, that when we say PTR plus 1, we don't mean plus 1, we mean plus 4. So you need to keep an eye on that. If it's a double, for example, and you say 1, it might increment by 8. If it's a character, it might increment by 2. So that's very deceptive, that plus 1 doesn't mean plus 1. Let's talk about passing an array to a function using pointers. We've declared and defined an array here of 4 integers, and I've run the code down to this position here. And you can see in the locals window here we've got our array 0, 1, 2, 3, 4 are the elements. And as it happens, I've got the memory window opened as well, and you can see that address is the address corresponding to that. And you can see my array is stored as 4 consecutive integers, each of 4 bytes long. If we take a look in a bit more detail here, this age here is in fact a pointer. It's a pointer to the start of the array. If we're going to pass our array to a function, then all we need to do is to pass the address of the start of the array. Well, this age is indeed a pointer, but be careful, it is actually a pointer constant, so that if we try something like this, it will cause an error, because you cannot increment a pointer constant. You can put a pointer equal to that. You can say PTR equals to AGE and then increment PTR, but you cannot increment a pointer constant. It's different from a pointer variable. PTR is an example of a pointer variable that we've been using, but age is a pointer constant. So let's say we defined or declared our function called dodo that we want to pass our array to. Just get rid of that, and we therefore, as you know, we always need a function prototype. So we're going to try and pass our array to that function. Well, we can call dodo, the name of the function, but what are we going to pass? We're going to pass the address of the first element. That's the address of the 1, as a matter of fact. You can see that down here. That's the 0, 1 is the first element, so AG is the address of the first element of the array. Just to emphasize that, you could actually, instead of age, you could use the address of AGE0, which is the address of the first element. Rather clumsy, but it does give you the idea. It's the address of the first element that you're passing. So the question then arises, what sort of variable, what type, is going to receive that argument? Well, the answer is it's going to be a pointer. So we need our asterisk to say that it's a pointer. But don't forget, we must also say that what it's pointing to, always. So we need, therefore, to, in our prototype, we need to do something similar to say what the parameter is that it's going to receive the argument. So indeed it's a pointer. So we could put in a variable here. We shouldn't really use the same name. We could use AG, for example, but it has a different scope, so we'll just use that for the moment. So that should work just fine. We might want to do something inside the array, change one of the elements. For example, in this case, this would be the 0, 1, 2, 3. That's the 4th element. So this element here should be made equal to 7. It's changed permanently because we're using a pointer to point to the exact address. Then this will be a permanent change to the array. The other way of doing that, using pointer notation, would be to increment the pointer by 3 and then say the contents of that is going to be equal to 7. So that should do exactly the same thing, and we could check that out if you like. We'll run the code down to there. We'll put a breakpoint in here and then run the code, and we single step up to this position. You can see the value of age has got 874. If you could just see that, you can see there's the array over here, and we're passing the address of the array, which is also 874, identical. So you're passing this address here is being passed from the main body to the function called dodo. So once we've got it now, let's see what happens when we F11. If you watch carefully, the array itself, which is this array here, if you watch carefully what happens, I'll F11, and now the contents of AG plus 3, you can see it's been changed to 7, which is a permanent change. So that's how we pass a function, pass an array to a function using a pointer. So once again, we have a pointer constant, which we sort of get for free, really. When we define our array, we get that AGE pointer for free, and we use that to pass the array, or at least the start of the array, to our function. The arrow notation, you might have seen this arrow notation somewhere associated with the pointers. Let me explain what it is. Let's say we've got our user-defined type, which is called part, and we're going to create an object. We're going to make this object on the heap, so we're going to use the new operator, and when we do that, to declare and initialize our object, new returns a pointer, so we therefore must declare a pointer to type part. And we've also got a method. Well, it's not a very useful method. We could use a constructor instead of that, but let's just say we wanted to set our value of I, in this case, using a pointer. Using a method rather than a constructor, but let's see how we would actually access that method. Now that we've got a pointer, now let us think. ptr.I. This is the usual way that we would access our ptr.put. This is the usual way that we'd access our method using the dot operator, but that's not going to work because this indeed is a pointer. It's not an object, it's a pointer to an object. So if we were to try that, it just won't work. So we need to think about this, we need to dereference our pointer first. So it's going to be the contents of PTR, which is indeed our object. So that works. So that's how we do it. We say the contents of PTR, which is the object itself, and we call the method put upon that object. Well, that's slightly clumsy notation. There is another way to do it, and which is simplified, and that's using the arrow notation. So basically we can replace this by the arrow notation. So that will mean exactly the same thing. So if you run our code, we should find that that sets the value, the I value of that to 3. Well, indeed, we need to pass the value of 3 rather than put that equal to. Let's correct that. So that should pass the value of 3 to that method. So if I run that to the breakpoint, and now if you watch carefully, if I F11, that should pass the value of 3, should be passed to J, which indeed is then passed to I.